Welcome everyone. For today's prep, we're going to look at, or start to look at, a technique for differentiating called logarithmic differentiation. And, well, we're really going to use some special properties of our log function. And we're going to start by looking at those properties. And the properties we have written are written here for natural log, but they work for all of the regular log functions as well. So let's read through the list. So we're going to suppose x and y are two positive numbers. And first, let's read through these, and then we'll kind of describe what they do. So the first property says if we have natural log of x times y, well, that's equal to the natural log of x plus the natural log of y. And if we have the natural log of x divided by y, well, then that becomes the natural log of x minus the natural log of y. And then finally, if we have the natural log of x raised to some power b, where b can be any number, well, that's the same thing as taking b and multiplying it with the natural log of x, just x. So what these properties do is, in some ways, they take complicated operations, or more complicated operations, like a multiplication or division or exponentiation, and convert them into easier operations: addition, subtraction, and constant multiplication. So what the first property does is we want to think about what's going on inside the log function and kind of compare that to what's going on outside of the log function. So for the first property, it's taking multiplication. So we're taking multiplication that's happening inside, and it's converting it into addition that's outside the log function. And then for the second property, it's taking division that's going on inside. So we have a fraction there, x divided by y, and it's converting it into subtraction. And then finally, we have raised to the power b going on inside of for the last property, we have the exponent b, and that's converted into constant multiplication outside. So it's taking these, essentially the log function kind of takes these more complicated operations and somehow converts them into these easier to manage algebraic operations. And we're going to use that to our advantage with derivatives, because we know from experience it's much easier to differentiate when we have addition, subtraction, or called constant multiplication versus multiplication, division, or exponents. And where these properties come from, they really come from, each of them comes from a corresponding exponent property. So probably worth mentioning it here. So we have our exponent rules as well. Definitely worth a mention. So what's the corresponding one for the first property? Well, what happens is if we have an exponent term where we have e raised to the x times e raised to the y, so we have multiplication going on between exponential terms, what that's equal to, we add the exponents. So that would be equal to e raised to the x plus y. And if the second property, if we divide exponential terms, so if we have e raised to the x divided by e raised to the y, well, we subtract the exponents. So when we divide, we subtract the exponents. And the third property that kind of matches up here is when we have e raised to the x and then that whole thing raised to the power b. Well, when we have multiple exponents like this, what do? We multiply the exponents together. So we end up with e raised to the b times x. And you can kind of see these three properties are analogous with the properties of our log function. So if we have multiplication of exponential terms, that gets converted into addition going on in the exponent. If we have division, that gets converted into subtraction in the exponent. And if we have kind of multiple exponents going on, well, we just multiply the exponents. And that's kind of what we're seeing here. We're multiplying the b and the natural log x. All right, so just a good review of some of our exponent properties and kind of give you an idea of where these log properties come from. All right, so let's put these into action now to help us simplify a derivative calculation. And for the prep, we're just going to look at this first example. We're going to do the second example in class. And the second example here, this is really where this technique is going to shine, because this function is really unlike any other function we've seen before. There's variables in both the base term and the exponent term. So this isn't really a power function, and it's not really an exponential function. So this function's kind of something a little bit different. So we'll save that for class. But instead, let's look at example 1. So here we have the natural log of x plus 1 over the square root of x minus 2. We want to differentiate this thing. And we have all the rules at this point to just kind of go through with it. So if we were going to do this the hard way, we could just use our general log rule first. So differentiate our way through the log function. Then when we get to the stuff inside, then we'd have to use quotient rule because we have a fraction. And then when we get to the square root term, we'd have to use our general power rule. So we'd have to, if we were going to differentiate this the long way here, we'd have to use chain rule to get through the log function. We'd have to use quotient rule to get through the fraction, and then chain rule again to get through that square root. The property of this log function, though, is really going to simplify it down, so we really won't have to use many of those. All right, so if we look at what we have here, we have the natural log of a fraction. So the first thing we can do is to simplify this function, rewrite this function using some of our log properties. And we know we have one for when we have a fraction. So what that property says is we can take the term on the top, the term on the bottom, and what the log function does is it converts that division into subtraction. So we're going to break apart this natural log. So we'll have the natural log of the top function minus the natural log of the bottom function. So that's just log properties. So we haven't done any derivative yet. This is just some algebraic properties of the log function. And that's a 1 there. All right. So we've used that second log property. Put a little 2 there, just to indicate which property we used. Now there's one more we can use, actually. So this square root term, we're able to use that exponent property. So if we think of this, we could first rewrite this as the natural log of x plus, well, the natural log of x plus 1. That one's good. That one's good as is. But we could rewrite that square root term as x minus 2 raised to the 1/2 power, with the 1/2 power inside of the log function there. And what that third log property allows us to do, when we have something getting raised to a power, what we can do is we can take that exponent and we can bring it out in front of the natural log. So in this case, if we use that third property, we're going to have still the same natural log of x plus 1, and then we'll have our minus, but then we could take that exponent of 1/2 out in front of the natural log. So we'll have 1/2 times our natural log of x minus 2. And that's the third property. So let's just pop back up real quick. We use the fraction to convert it into 2 separate log functions where we have subtraction. And when we have something getting raised to a power, we can bring that power out in front of the natural log. And I know that kind of feels like power rule, but this is not a derivative or anything. This is just an algebraic property of natural log. All right, so now with the function rewritten like this, now we can differentiate. So we'll call our derivative f prime. And let's start with the first term. So we have natural log of x plus 1. So we're still going to have to use chain rule here, but there's not going to be as many other things going on when we do it. So for this first one, we got to differentiate our way through that log function. So when we differentiate natural log, we get the reciprocal of whatever's inside. So in this case, 1 over x plus 1. And then we multiply by the derivative of what's inside. So we're going to multiply by the derivative of that x plus 1. And that's our general log rule for chain rule. That flavor of the chain rule. And then we got our minus 1/2. So the 1/2 is just a constant multiple. And we do the same general log rule for that other log term. So we do the reciprocal. We got to differentiate our way through the natural log. So we do the reciprocal of what's inside. So we'll have times 1 over x minus 2. And then we're going to multiply by the derivative of the term inside the parentheses. So the derivative of x minus 2. And if we finish differentiating, derivative of x plus 1 is just 1. And then derivative of x minus 2, also just 1. So we kind of get lucky here, but you don't want to forget chain rule, the general log rule here, because sometimes you might have some contribution to this. But in this case, this just ends up being 1. This just ends up being 1. So kind of a freebie. So we can finish it off. So the first term ends up being 1 over x plus 1. And then we have minus 1/2 times 1 over x minus 2. And there's our derivative. All right. So we're going to see how we can use kind of this similar strategy of log functions and using those algebraic properties to differentiate something a little more exotic like this. So we'll see that in class. Now, one more thing before we go. Just going back up to our properties here. These properties, there's only properties if we have multiplication or division or exponents. So there's no properties if we have addition or subtraction inside the log function. So probably worth a mention here. So note, no properties for addition or subtraction inside natural log. So only multiplication, division, or exponents. So if there's addition or subtraction going on inside the natural log, that's kind of where we get stuck. So if we go back to that example, I couldn't simplify natural log of x plus 1 any further because there's no more multiplication going on in there. I get down to a point where it's just addition. And then same thing here. I can't really simplify this any further because I get to the point when it's just subtraction. So that's as far as we were able to simplify these. Okay, so like I said, we'll get a little more practice of this in class. So we'll see you then. Bye-bye.